Exercise set 1.4. Applications. Two-variable linear systems of equations. Standards of solutions. Define all variables. Explain the source of any newly introduced equation. Assess the correctness of the solution by performing two types of checks: a check of the math problem solution and a check for sensibility in the real world. Of the two checks, the latter is the more important. Be reminded that the most likely source of error in an application problem lies in the translation from the real-world problem to the math model problem, thus the importance of a sensibility check. Calculator usage is required. Exercise 10. A 7,500-gallon tank has two inlet pipes and three outlet pipes. One inlet pipe has a flow rate 5 times that of the smaller inlet pipe. The three outlet pipes have equal flow rates. With all pipes open, it takes 54 minutes and 24 seconds to fill an empty tank. If the smaller inlet pipe and two of the outlet pipes are closed, it takes 1 hour and 14 seconds to fill an empty tank. If all three outlet pipes are closed and both inlet pipes are open, how long will it take to fill an empty tank? Round final answer to the nearest second. Okay. Variable choice. Let's see here. Oftentimes choosing the quantity asked for as one of your variables is effective, but that would mean having our variable being time to fill an empty tank under conditions 3 outlet pipes closed. Okay, that would be hard to work with. Clumsy. Alright, more fundamental. Okay, flow rates in the pipes. So, for instance here, let's go ahead and say let x equal the flow rate in the smaller inlet pipe. And when you have flow rates, there is the issue of directionality. This diagram, I think we should probably use this. We'll make the positive x to be in the direction shown, and eventually we'll have some flow rates in the outlet pipes. We'll make this represent a positive value. Okay, so x is the flow rate in the smaller inlet pipe. Positive direction as illustrated, and the units of measure, okay, flow rate, gallons, looks like the certain choice for volume. Time, looks like, why don't we choose minutes, and then we'll stay with minutes throughout the problem. So the units of measure here will be gallons per minute. Okay, now something actually we can compute in 2 seconds. It's a direct implication, and that's the flow rate in the larger pipe. Since it's 5 times that of the small inlet pipe, it's an easy matter to just say that this definition simply implies that, because of this information here, 5x will equal the flow rate in the larger inlet pipe, positive direction as illustrated. Gallons per minute will be the unit there. Okay, and now outlet pipe. They're all the same, so we can say let rather y equal the flow rate in, we'll say, one outlet pipe. Positive direction as illustrated, gallons per minute being the units. Okay. Now, what kind of information do we have that would lead to an equation? Okay. This sentence, with all pipes open, it takes 54 minutes and 24 seconds to fill an empty tank. Okay, let's work with that. If all pipes open, time to fill an empty tank is 54 minutes 24 seconds. Okay, how can we work with this? Well, there's a real basic formulation of fluid flows. We can go with the idea that volume equals the flow rate times time. It's kind of similar to how when objects are moving, distance equals speed times time. It's another one of these kind of basic ideas. And how can we get it to work here? Well, the volume of this tank is known, 7,500 gallons. Flow rate. Now, all the pipes are open. So, flowing to fill the tank here are the inlet pipes. Now we have X for the smaller one, 5X for the larger one. Now these outlet pipes, when they are actually taking water out of the tank, draining it away. So that's a minus 3Y, 3 identical outlet pipes flowing like this in the direction shown are going to cause the flow rate to decrease. Okay, how about that time? Alright, 54 minutes, 24 seconds. Now we're going to stay in minutes here, so 54 plus, we'll have to say 24 over 60 seconds. Okay, got an equation. Equation 1. Great. I suppose we may want to simplify this a little bit before we move on looking for more information. Okay, x and 5x. Okay, that's 6x. And this 24 over 60 simplifies a little bit. A factor of 12 is common. 2 and 5. 2/5. That would be 0.4, since having an exact decimal number might make this convenient here. Alright, so we could say 7,500 equals 6x minus 3y times, and this ends up being just a single number, 54.4. Alright, we can call this equation 1a. Alright, let's see. Now there's another idea we can use up here. It says that if the smaller inlet pipe and 2 of the outlet pipes are closed, it takes 1 hour and 14 seconds to fill an empty tank. Okay, let's start putting bullets here to organize this solution. It's rather complicated. Okay, so here we are. Let's describe what we're going to do here. We're working with the idea that if smaller inlet pipe and 2 outlets closed, emphasize closed, it takes the time to fill will equal 1 hour and 14 seconds. Okay, we like minutes, so in other words 60 minutes and 14 seconds. Okay, now let's see what we can do with that. As before, volume equals flow rate times time. So in this case, let's see, the volume is still an empty tank. That would be 7,500 gallons, equaling. Now, what have we got here? A smaller inlet's been closed. So the larger inlet is giving us 5x flow rate. 2 outlet pipes are closed. Well, one of them's still open, so we're still losing a y flow rate out of a draining an outlet pipe. And now the time is 60 plus 14 over 60. Okay, this could be equation 2. Little cancellation here, just a factor of 2 if you even want to bother. It's not going to help us much. I think I'll just leave that alone. Okay, there we are. Now, taking a look at our information otherwise, there is really nothing left to translate. This is it here. And if we look at the two equations that we're finally working with, the 1a and here in 2, they're both linear. Okay, so we could observe that this math problem is a system of linear equations. So observe observe that equations 1a and 2 constitute a linear system of equations. Okay, we're pretty good at this. Let's solve this, and let's go with calculator usage, which means we'll need to solve for the y's in each of equation 1a and 2's case. Let's look at equation 1a. Let's solve for y. We'll need to divide both sides by 54.4, subtract 6x from both sides, and then divide both sides by -3. Okay, let's try that. We'll have here y1 equaling, we have, alright, here's 7,500. It's divided by 54.4. Then there's that minus 6x, but then we multiply both sides by -1. So then the 6x ends up like that. And then it's divided by 3 to finish out. Okay. In the second equation's case, solve for y here. Alright, divide both sides by the 60 plus 14/60ths. Subtract 5x. Multiply both sides by -1. Y sub 2 could equal 5x minus 7,500 over 60 plus 14 over 60. Okay, looks like it's time to go to the calculator. Okay, here at the calculator, we could go to the y equals 2 menu, and for our y1, we've got parenthesis 6x minus 7500 divided by 54.4 parenthesis divided by 3. For y2, we've got 5x minus 7,500 divided by, in parentheses, 60 plus 14 divided by 60. And another parenthesis. Alrighty. Now, selecting a coordinate system here. Thinking about x and how it is the flow rate of a small inlet pipe. Let's see here. These this 7,500 gallon tank. Just let's see, what if X was 100 gallons per minute? That would be very large. By itself, the little pipe could fill a sealed off empty tank in 75 minutes. Okay, that might be some kind of a starting point for an X, a sensible X here. Let's go with that just to get some kind of window set up. And we can go 0 for X min. And let's just take a 100 for a virtually arbitrary positive large number for X just to get started. Let's have the y-axis figured out by the calculator by going zoom fit. Okay. Something in there. Let's zoom in. We really want to make sure we have positive numbers. Part of the sensibility of this would be to have positive values for X and Y. Otherwise, we have a situation that probably isn't expected at all for an inlet pipe and an outlet pipe. But let's see what happens. Maybe those are positives. Okay, zoom box, perhaps. And let's see, move the cursor over to where it can be a corner of a box. Let's see, I think maybe here for one corner. And then we'll come over and up. Let's see what's going on in that rectangle there. Okay, it's nice to see that X and Y are coming out to be positive numbers here. Now we can go ahead and get them calculated. That'll be a matter of going second, calculate, intersect. That's a good first curve, that Y1, enter. That's a good second curve, that Y2, enter. As for a guess, maybe move the calculator graphing cursor over a bit right there, looks about right, enter. Okay, so we have these numbers here on the calculator for the math problem. Let's, for now, maybe we go to our paper and start thinking about the situation for a minute here. Okay, so here's what we have here. We right now have on this calculator an X equal to 26.18663, approximately, and the Y approximately 6.4173.774. Okay, and the calculator has even more decimal places than this. It just shows a limited number of them on a graphing screen. If we go to the home screen, we can get more. Alright, for us to think further though, this is adequate. Alright, so we have this solution to a math solution to this system X and Y. However, let's think about the actual question that we're being asked in this. The question ultimately asks us, how long will it says, if all three outlet pipes are closed and both inlet pipes are open, how long will it take to fill an empty tank? Okay, so let's take a look at the question here. If all three outlet pipes are closed and both inlets are open, okay, what have we got? Well, as always, we can start with our general formulation again. Volume equals flow rate times time. And in that case here, the volume is the empty tank, 7,500 gallons. The flow rate, okay, now it's all three outlet pipes closed, both inlet pipes open. So we have then an X for the small inlet plus a 5X for the large inlet. There's nothing being drained. And then times time. Okay, so it looks like our time will equal 5X and X is 6X, 7,500 over 6X. And don't use like some decimal approximation right now in the middle of this problem. Even this is not good enough. Let the calculator take over using the full power of its like 12 digit number that it's holding to do the calculation. So this will equal, and now it's time to go to our calculator to even finish this out here. Okay, so on this calculator, let's go to the home screen and let's perform that important computation. 7,500 divide by, now to divide by all of 6x, be sure to use parentheses here. 6x, keep all 6x in the denominator. You know, if you just put in a 6x without the parentheses, the calculator will go left to right in order of operations. In other words, it'll do 7,500 divided by 6, and then it will multiply by the x. So you need the parentheses to keep all 6x in the denominator. Okay, back on to our problem. Let's compute this. Okay, now there's the time in minutes for this tank to be filled. Again, thinking back to the way the question's worded, or the way it's stated, is that it wants us to round to the nearest second. Okay, so let's see. We have our minutes here. Let's get our seconds. We can do that by subtract the 47 and take this leftover fraction, multiply it by 60 seconds per minute. Okay, here we are ready to put a formulation together. We're going to have a time of 47 minutes, 44 seconds. Okay, let's go back to our paper. Okay, so as we had said, we have here 47 minutes, 44 seconds. And now to make sure we're fully answering our question clearly, equals time to fill tank with all three outlet pipes closed and both inlet pipes open. Okay, this is the core conclusion of this question. So I'll put it in a prominent cloud. Okay, now let's check this over. Since the check, I want to clearly show our space division here. Okay, check. Two parts to this check. One, let's make sure we have just the math in order. Okay, for that, as usual, let's substitute our calculated x and y into the original equations. Okay, so go back to equation 1, and the right hand side has all the variable items in it. So let's check out this side here. This means we need to take a look at x plus 5x minus 3y times 54 plus 24 over 60. Get a number there. Hope to see 7,500. And for the second equation, okay, its right-hand side has all the variables in it. We'll worry about that then, and that means 5x minus y times 60 plus 14 over 60. See what happens there. Hope to see 7,500. Okay, off to the calculator. Okay, here at the calculator, let's go ahead and clear this home screen for a minute and begin with that first equation. We've got parenthesis x plus 5x minus 3 alpha y parenthesis times, okay, so another parenthesis, 54 plus 24 divided by 60 parenthesis. Enter. Okay, good. 7,500. Second equation. Parenthesis 5x minus alpha y parenthesis 60 plus 14 divided by 60. Wait, there's a extra 4 that's appeared there. Delete. Okay, need a parenthesis. Okay, let's enter. Okay, great. 7,500. Just what we were hoping for. Back to the paper. Okay, so this comes out to be 7,500, just as the original first equation. This came out to be 7,500, just as in equation 2. Alright, so the math check looks pretty good. How about the sensibility? Alright, one thing I had mentioned before in looking at the graph, and it's something that is good to see, and that's that both x and y are positive numbers, are positive value. So it's nice to see that, because you sort of want to see your inlet pipes having water flow into the tank, and you really like to see the outlet pipes showing water going away from the tank like would be normally expected. So that was good to see. Another thing, what about this this final number here, 47 minutes 44 seconds? What should we expect of that? The conditions were all outlet pipes were closed and both inlet pipes open. Okay, what we expect here then, since this is having the tank being filled at the fastest possible speed. Okay. Conditions of both inlets open and all outlets closed should yield fastest fill time. And let's compare. The time here was 47 minutes 44 seconds. Look at the other scenarios that were described in this problem. The first one was 54 minutes 24 seconds. The next one talked about was 1 hour 14 seconds. So this is indeed consistent with the other situations. This is consistent with the other scenarios of 54 minutes, 24 seconds, and the 1 hour, 14 seconds. Faster than all of these. Good. Okay, so the answer can sort of feel correct as well. And we are all set here. Looking good. Exercise number 12. A designer is sketching plans for a conference table. The table will have a rectangular region flanked by a pair of semicircular regions, as illustrated. To achieve comfortable seating, the perimeter is to be 50 feet. For aesthetics, the sum of the areas of the semicircular regions must equal the area of the central rectangular region. Calculate the dimensions of the central rectangular region, rounding to the nearest inch. Okay, what to do here for some variables? Well, when there's a nice diagram provided, you can use it to help define your variables. For instance, here we might choose to say, let x, y be rectangle dimensions as illustrated. Maybe we choose x to be along here, y along here. The units of measure for those, okay, since our perimeter is in feet, that's probably the easiest to work with. So here we'll say feet. Of course, when we ultimately record our final answer, we'll record the number of feet and the fractional part of the feet in terms of inches to meet this requirement here. Okay, otherwise what can we do? Well, looking over the paragraph here, here's a sentence that seems to lead to an equation. To achieve comfortable seating, the perimeter is to be 50 feet. Okay, so let's go with a little bullet here and say the perimeter is to be 50 feet. Okay, let's try to think about what the perimeter is of this table, the distance around it. It will consist of 2 of these rectangle lengths plus a semicircle and another semicircle. Okay, so it looks like we have 2 semicircles plus 2 rectangle sides equaling 50. Now, what about this 2 semicircles? If we have 2 semicircles, then we have a complete circle. So we might recall for a circle, a general formula you might think of: circumference equals 2 pi r. Or sometimes rewritten in another form, you can say pi times d. d is the diameter of the circle. Alright, so in that case, here we could have the circumference would equal pi times y. Okay, so this allows us to then take this and write this as pi y plus, well, x and x. 2x is equal to 50. Alright, here's our equation 1. Now, what other information have we got? This sentence: for aesthetics, the sum of the areas of the semicircular regions must equal the area of the central triangular region. Central rectangular region. Okay, let's analyze that. So, sum of semicircles must equal rectangle, basically. Okay. Semicircle areas, I guess. Alright, what about this? Well, there's two semicircle areas. That means the area of a circle. So maybe we recall for a circle, a very general famous formula, area is equal to pi r squared. Now here, in our particular case, well, y is the diameter of the circle, so y over 2 becomes a radius. So we have a equal to pi times y over 2, playing the role of the radius, being squared, giving us, finally, a pi y squared over 4. Okay. Now that gives us the area of the sum of the semicircles. Let's go on and write our equation that goes along with this statement here. The pi y squared over 4 has got to equal rectangular area. That would be x times y. Okay, here can be equation 2. Now, this equation here, you may decide to simplify matters a little bit. Maybe multiply both sides by 4. Get rid of the fraction. Divide both sides by y. Take out a y here. And y cannot equal 0 anyway because it's physically a dimension on a table, so it can't be 0. Alright, here we go then. This would leave us with pi y equaling 4x. This could be equation 2a. Alright, let's see what we have here. Any other information? No, I think we've accounted for everything in this paragraph here. This is going to be our math problem, what we have here. And if you look at the equation 1, linear in x and y. Equation 2, also linear in x and y. Okay, so we can observe that the math problem is a system of linear equations. Two variable. Alright, so we can start working on that. Okay, to begin our solving of the math problem, let's consolidate it right here. Here's equation 1. Okay, maybe I'll put it in standard form. So that's a 2x plus pi y equals 50. Equation 2a, sitting here. Let's put it in standard form too. So then we could have a 4x minus the pi y equals 0. And at this point, it looks like this would be really easy to do manually. It's because the elimination is just ready and waiting for us. At least the first part. Okay, here we go. Basically add the equations together, roughly speaking. 2x and 4x, 6x. Plus pi y minus pi y, 0 y's. The y's are eliminated. 50 and 0, 50. Okay, so now we're left over with an x equals 50 over 6, which, okay, gets a little simpler. 25 over 3. Alright. You know, you could probably spot this 25 over 3 as being 8 and 1/3. And since we are eventually to go to inches in the end, you could even go here and say this is 8 feet, 4 inches, exactly. Okay. Now, as far as y goes, we need y to the nearest inch. It's probably time to go to a calculator, and let's see what will we go there with. Maybe use this equation to get it. We can say y would equal 50 minus 2x divide by pi. And see what comes out there. Alright, time for some calculator work. Okay, at the calculator, we might start with doing the 25 divide by 3, and we can take a look at that number, and sure enough, there is the 8 1/3 we were expecting, which is 8 foot 4 inches. Okay, now we should store that to x, because we would like to use the calculator to assist in checking. So store to x, enter. Now it's in there. And that will also facilitate this next calculation, which is our y that we have computed here. We have got parenthesis 50 minus 2x parenthesis divide by pi, divide by second pi, and enter. Alright, now I want to have this nice number around for future checking, so I will store it to y, store to alpha y, got it, and let's also get ready to record a dimension to the nearest inch. Right now, right there, we see y in terms of feet. Now, let's take off the 10 feet and convert the fractional leftover into inches, so we can subtract 10. And then take this leftover and use 12 inches per foot. Okay, it's going to be 7. Alright, time to head to our paper to do a little recording of the situation thus far. Okay, so on our calculator, we've found this y to be 10 feet, 7 inches. And to record our answer, something very geometric like this conference table, we would really do well to give a final answer with a scale diagram. Okay, so from here we can claim the conference table has the following rectangle dimensions, and our scale for this drawing could be 1 centimeter equals 2 feet. Let's try that. Now we need a y of 10 foot 7. Okay, that is decimally speaking 10 foot 6, which would become a 5.3 centimeters. Okay, now we want to have an x. You can use this triangle to get a nice 90 degree here. And this is the, let's see, 8.33 divided by 2 gives us about 4.15 centimeters on the scale diagram here. So that would be about there. Okay, and could repeat this down here. There. And then here, another 5.3 centimeters. see, while I'm here, should mark the midpoint of this line. To draw the entire table would look kind of sharp and give us a check as well. So let's see, this is 5.3, 2.65 is our center mark. Over here, same thing. 2.65, about there. Okay, then to draw a semicircle or two, get a compass, of course, and mark off a radius. Let's see how this is going to look. Okay, it's a little off in that direction. Split the difference. Okay, about there. And on this side, same thing. Okay. Let's put our rectangular dimensions in here. We have across here, okay, 10 feet, 7 inches for the y dimension here. And across here, we had a 8 foot 4 inches. Okay, and this is sort of the major conclusionary part of this problem. Block it off down here. Okay, and finally, let's start checking things over. Two parts to this check. First, a math check. And what we'll do is we'll substitute into the original equations. Okay, going back to the first equation 1, its left-hand side was pi y plus 2x. Let's see what that turns out to be. The second, okay, maybe we call this equation 1. And then we had equation 2. Now for equation 2, had variables on both sides. So the original left-hand side, LHS, was equal to pi y squared over 4. And the right-hand side, that was equal to xy. We'll see what that is. See what this is here. Okay, it's time to go to the calculator. Okay, once at the calculator, we can go ahead and start trying out these equations. Remember, we've already put the x and y stored into the x and y locations in the calculator, so we're ready to go. First equation, second pi alpha y plus 2x, enter, 50. Okay, nice. Alright, now equation 2. The left-hand side was originally second pi y alpha y squared, and that was divided by 4. Okay, that supposedly is the sum of the semicircular region areas. Now let's get the right hand side of that equation, which is the x times y. X alpha y. Cross your fingers. Wait. Okay. Okay. Good. Ready to go back to our paper. Okay, on the calculator we found this to equal 50, just as in original equation 1. Looks great. Here we found this to, well, about equal to 88.4. And this came out about equal to 88.4 as well. And that's the kind of thing that gives us the check on the second equation. It's in order. Alright, how about sensibility? Okay, now we have a nice scale diagram of the conference table right before us. We can just sort of looking things over, seeing if it looks right. Okay, so by inspecting the scale diagram, the perimeter, without being all too exacting here. All right, so here we are. Here's 8 feet and 8.5 feet across here. Well, here's a semicircle. That much is about there. Okay, so maybe there's 8, 16, 24, about 25 feet or so around there. Back the other way, same idea. If this is 8 feet, then approximately, just quickly, about there is about 8 more feet. There's about 8 more feet. This, has the appearance of about a 50-foot diameter. And what about the areas? If you visually look at this rectangle, you visually compare it to these two semicircular regions, it looks like the sum of these semicircles is about equal to the area of the rectangle. So really, with this picture, these numbers here actually seem to look really good. Okay.